All right, good afternoon, class. I'm sorry that I'm not able to be in class today. I'm at a cross-country meet, but I'm going to record this video lecture of our notes, and I'm going to start moving through it pretty quickly. So if at any time I'm going too fast through the notes, you can just pause the video. So you should have picked up the hard copy of these notes off the back counter. So if you don't have the notes, pause the video and go grab them right now. And then the second thing that you're going to want to have is either your graphing calculator. I don't have a great way of showing you how to use your graphing calculator on my iPad. So remind me on Monday in class to kind of go over the specific functionality of your graphing calculator. But for today, just do a Google search of Desmos graphing calculator. And then this is what I'm going to show you kind of how to use on this video today. But again, remind me in class on Monday and I will go over how to use your handheld graphing calculator. All right, so here's what we're doing today. We are talking about function families, and there's many types of function families in the math world, but today we're just talking about 4 different kinds. The 4 that we're talking about today are linear, which you guys are probably very familiar with from 8th grade. We're also talking about absolute value functions. We've talked about those a little bit this year. We're going to talk about quadratic functions, and then the last kind we're going to talk about are exponential functions. Each of them kind of have their own characteristics, and we're going to look at what those are. So to get started, on the homework today, you're going to be asked to identify functions basically in 3 different ways, or there are 3 different ways that you can identify function families. Here's how you can do it. Number 1, you can simply look at their function notation or what their equation looks like. So that's one way that you can tell what kind of function family a particular graph is in, or a particular function is in. The second way that you can tell what kind of function family a function belongs to is by looking at the graph. So like the graphical representation of the function on the coordinate plane. And then the third way is by looking at a table of values that represents the function. All right, so we're just going to hop right in here. The first one we're doing is a linear function, and all the functions you're going to look at today pretty much are in the form f of x and then equals something, like some other thing over on this other side. Well, the f of x part, that's just simply in function notation, and as I've said a few times in this class, another way of writing f of x is y. So you could just think of this function as the equation y equals 2x plus 3. And if you do that, I think most of you will be very familiar with this and kind of remember it from 8th grade. But here's what I would like you to do today. So go to your Desmos graphing calculator and you're going to type in 2x plus 3. And sure enough, we have ourselves a nice looking linear function. But I want to do a little bit more than that. So hit the gear looking button right there. And then you've got a couple options, and the one that I would like you to hit is the table. Now, when you're doing this on your graphing calculator next Monday, you'll notice that there's infinite number of values that we can use from the table. Like you can scroll on your graphing calculator forever and ever and ever. This particular table starts at -2. And so I think that's actually where we're going to start our table as well. Actually, here's what I would like you to do. So go to your table on your notes and copy all of these values starting in the second row. So in the second row, -2, -1. Okay, so I just copied the table of values that I saw on Desmos. And here's the reason why I had you leave the first row open. On Desmos, if there is a specific input value or an X value that you're trying to find, you can click into the X value box, hit backspace, change it to whatever you're trying to find, and it tells you what the output is. So I just plugged in an input of -3, and it told me that the output is also -3. So I'm going to go up to my table and I'm going to fill that in. Okay, before I proceed any further, I do want to point out what I'm getting ready to say. We're not going to do a lot today, but I just want to point this out so that you have an understanding that this is what's going on. So if we didn't have a graphing calculator, we could take any input value in the whole wide world and we could plug it into the function, and we could say, for example, f of -3 equals 2 times -3 plus 3, just like we've been doing in class the last couple days. You would then evaluate it, and sure enough, as an output, you would get, -3. And so you can see that's the same thing that we got right there when we used the Desmos graphing calculator. So you might be saying, well, why don't we just plug them all in by hand and not use a graphing calculator? You certainly could do that. The disadvantage would be that it would take you a lot more time. But I do want you to have an understanding that, hey, these are input values that we can plug into the function and solve for an output value. Today, we're just kind of using technology to assist us. All right, so here we go. Let's plot these points. And again, pause the video at any time if I'm going too quick. All right, go ahead and connect those points. Actually, I can do better than that. I am going to use a ruler or a straight edge. Cool. All right, so that is a linear function. Here's a couple more things you need to know. So how would you identify a linear function from its function or its equation? Well, you would be looking for things in the form y equals mx plus b, or f of x equals mx plus b, or even just something that said like y equals, y equals 5x, something like that. All right, what do their graphs look like? Well, these are the ones that you're very familiar with from 8th grade. They simply are lines. That's where the word linear comes from. So they can be going all sorts of different ways, but lines, that's what we're talking about. Last, what is happening in the table? Well, as x changes, so if x either increases or decreases, y changes by a common difference. And so what that phrase common difference means is it either goes up or down by the same amount. If we go and look at the problem we just did, I think most people can probably see that it's going up by 2. But here's one thing I want to do real quick because it's going to come in handy in a little bit. The way that you kind of officially find the common difference, so like in this table, it's pretty easy to see that it's going up by 2. But if you wanted to calculate this mathematically, like really crunch the numbers, here's how you do it. You take a value in the table, so I'm taking -1, and you subtract the value before it. So -1 minus -3 is going to give me the common difference of those two terms. Well, what happens with the double negative? It turns positive. -1 plus 3 is 2. The common difference of those two numbers is 2. If we move on, we could do 1 minus a -1. So that's this number subtracting this one. 1 minus -1 is 2. And then from there on out, I think it's really easy to see. 3 minus 1 is 2, 5 minus 3 is 2, 7 minus 5 is 2. So that problem definitely has a common difference of 2. Okay, that is our first function family, linear functions. I'm going to start trying to move a little quicker here. The next one is what's called an absolute value function. So go to Desmos and hit the button that looks like it has an A and it has 2 absolute value bars on either side. Hit X, There's your absolute value function. It looks like the letter V. Hit our table of values. All right, so let's go write those. And then again, I left this first row empty because I want to go back and I want to plug in -3. And by the way, there's no like specific rhyme or reason to -3. I could plug in anything for the input. -3 is just the next lowest value after -2 that the table didn't have in it already. So from there, let's go ahead and plot these points. All right, so if you plotted all these points, you might notice, well, hey, that kind of looks uneven or it looks unbalanced. Well, one of the properties of an absolute value function or its graph is that it is symmetric or it's symmetrical. And if you know that, then you should be able to say to yourself, well, hey, there needs to be a point right there. And there does. From there, we're just going to connect these using lines. And that is an absolute value function. All right, what do you need to know about it? Well, here's how you're going to identify it from an equation. You would be looking for something in the form y equals the absolute value of x, f of x equals the absolute value of x, or literally anything in the whole wide world as long as it has that absolute value expression. So that is kind of the distinguishing characteristic of an absolute value function or an equation, is if it has the absolute value symbol. Next, what do their graphs look like? Well, we already identified and said that it looks like a V. That is true, but if you have a negative in front of like at the very front of the problem, if you have a negative, what it does is it flips the graph upside down. And so you could actually have an upside down V. All right, the table, this is perhaps one of the trickier things that we'll look at today. Not too bad at all, but so here's what I mean. So here's what's going on with the table. As x changes, the y value changes by a common difference up to a turning point, and then the sign changes of the common difference, and it continues. So sorry, that's an awful lot there. You can pause the video to write that down. So what does this say? It says, as x changes, the y value changes by a common difference up to a turning point, and then the sign changes of the common difference, and it continues. So what the heck does that mean? Well, here's what it means. It means, as you can see in this graph, this absolute value graph, our common difference, we are decreasing by 1, decreasing by 1, decreasing by 1, decreasing by 1, boom, we hit a turning point, and then all of a sudden we start increasing by 1. So we were decreasing by 1 to a turning point where the sign changes to positive, and then we start increasing by 1. And if you look at our graph, that makes a whole lot of sense, because as you come down the left-hand side, it's decreasing by a common difference. You hit this turning point right there, and then it starts increasing by a common difference. Basically the same common difference, just positive instead of negative. Or if you had an absolute value function that was flipped, it would be the exact opposite. You would be going up by a positive amount, and then you would be decreasing, so a negative amount. In any event, that's what you are looking for an absolute value function. All right, rolling right along. We got two more of these, and then the last part of notes goes really quick. So the next one is what's called a quadratic function. And sometimes you will hear math teachers, me included, refer to quadratic functions as parabolas, or at least the graph of a quadratic function is called a parabola. And it's another word that means the same thing. So if you hear a math teacher say a parabola, they're talking about a quadratic function. Well, what does a quadratic function look like? Here's what it looks like. Let's go ahead and hit X, hit the button that says a to the second power. And a quadratic function looks like a U. That's what it looks like. So let's go get ourselves a table of values. So I think this time I'm going to mix it up, and I'm actually going to start at -2 this time. So one of the questions I got on the homework today, the other 9th grade honors classes who had this assignment, was like on the homework, students were asking me how to know where do you start your table? You know, do you start at -3? Do you start at -2? What do you start at? The answer is, the response is, it doesn't really matter where you start your table. You just want to pick X and Y values that are going to fit on your coordinate plane, whatever you're given. So like in this case, it looks to me like we have a coordinate plane that basically goes 7 unit squares in every direction. So I'm just going to start my table anywhere where I feel comfortable that those points are going to fall in the graph, or pretty darn close. So you'll notice that I have an empty row right here. Well, I'm going to go back to Desmos, and this time, instead of plugging in a -3 like I did in the last couple problems, I'm going to plug in a +3, and it gives me 9. Cool. Okay, so let's take those points and let's plot them. Okay, so the point 39 is off our graph, but I think we can estimate it to be, I don't know, maybe about like right there or something, approximately. One feature of a quadratic function, just like the absolute value functions that we just looked at, is that they are also symmetrical. And so the way that can help you is that it can kind of help guide you to placing some other points that maybe weren't part of your table. And I like to always try to keep things symmetric in terms of the number of points that I plot. It's not required, but it's kind of a good practice. All right, so there we go. You have just graphed probably your first quadratic function. From there, we're going to fill in these 3 boxes. So what would you be looking for equation-wise or function-wise for a quadratic function? Well, it's anything that looks like f of x equals x squared. It could be y equals x squared. It could be f of x equals ax squared plus bx plus c. It could literally be anything in the form of an equation or a function that has a variable of x taken to the second power. So you'll notice in every single one of these examples that I just wrote, every single one of them has an exponent of 2. 99.9% of the time in math, if you see an exponent of 2, generally speaking, you are talking about a quadratic function. So that's kind of the giveaway that you'd be looking for. What do their graphs look like? Well, generally speaking, they look like U's. The only exception to that would be very similar to an absolute value function. If you have a negative at the very front of this function, you guessed it, it's going to flip the function upside down. Oh, that's pretty poor U. It flips the function upside down, and it's an upside down U. Okay, the table. So back on the table for absolute value, I said something like, oh, this is going to be the toughest thing we do. This was a little tough, but this, in my opinion, is actually probably the toughest thing that's in notes today. So here's why I say it's tough, specifically for quadratic functions, because it's not real evident at the very beginning. So here's what you're going to be looking for. You're going to say, as x changes, y values change by, by a common second difference. As x changes, or I could have said as the x values change, but as x changes, y values change by a common second difference. What in the world does that mean? Well, here's what it means. Right next to this table, I would like you to write first difference. And the way that you find the first difference is basically what I was showing at the beginning of this video, or on when we were talking about linear functions. So take any point, any coordinate value, so I'm going to say 1, and you're going to subtract the number before it. So in this case, 1 minus 4, the difference of those numbers is -3. I'm then going to take 0 minus 1, the difference is -1. I'm then going to take 1 minus 0, the difference is 1. I'm going to take 4 minus 1, the difference is 3. I'm going to take 9 minus 4, the difference is 5. All right, so some of you may be having kind of a pattern that's forming in your mind when you're looking at these numbers right here, and that's great, but I want you to take a step back for a second and just answer this simple question to yourself. And the question is, are these numbers that I'm drawing arrows to, are they the same numbers, yes or no? Pause the video and answer that question. Okay, hopefully you said, no, they're not the same number, because they're not. This one's -3, this one's -1, this one's 1, this one's 3, this one's 5. Those are not the same number. They are different numbers. Therefore, here's what I'm getting at. The first difference of this table is not the same. But if we go and look at our definition, it says something about the second difference. That's weird. So here's what the second difference is. I want you to draw another column. And what the second difference is, it's the difference of the differences, which is a really wacky thing. So what would the difference of the differences be? Well, just like we did a second ago, take a number. So for example, take -1 and subtract the number before it. So -1 minus -3. But what happens is the double negative becomes positive and you have a difference of 2. Let's move on. Let's take 1 minus -1. That's this number right here and this number right there. Those are the two that we're subtracting. 1 minus a -1 is 2. Let's take 3 minus 1. It's 2. Let's take 5 minus 3. It's 2. I want you to pause the video and ask yourself this simple question. Are these numbers the same that I have just circled? Yes or no? Pause the video. Hopefully you said yes, they are the same number because every single one of them is a 2. And so what I'm getting at is, in terms of our definition, it says as x values change, y values change by a common second difference. So in my opinion, this is one of the trickier things in notes and on the homework today. And it's, to be honest, it's a little bit of a pain because you can't just examine or look at the first difference. You actually have to find the difference of the differences, which is called the second difference. And once you've done that, if it's constant the whole way, then that would be enough information to tell you that you have a quadratic function. Okay, moving on. Our last kind. This is called an exponential function. So let's go to Desmos, and we're going to go 2. Hit the button that says a to the b power. So 2 to the x power. And then let's hit our table. And let's start at, let's start this one at -2. All right, I want to go fill in that last value. So I'm going to go back and I'm going to plug in 3, and it gives me 8. All right, I then have a table of values. So this is the first time we've encountered any decimals, but not to fear, you can just go ahead and estimate those. All right, so negative 2.25, that would be about 1/4 of the way up the unit square. Negative 1.5 would be halfway up the unit square. 0, 1, 1, 2, 2, 4, and 3, 8 is off our graph, but it's approximately right here. So before we connect these points, making a smooth curve, I want us to go back. What if we came up here and what if we did plug in negative 3? It's 0.125. Interesting. So if we were going to graph that one, negative 3.125, it's even closer to the x-axis. If you had a graphing calculator where you could kind of scroll through the table of values quickly, which I can kind of show you how to do on Monday, what you would notice is that these values just keep getting smaller and smaller and smaller as they approach the x-axis. But this line never actually, or this exponential function never crosses the x-axis. And so let's go back and let's just kind of get in the habit of drawing a line that kind of hovers over the x-axis. And then it goes up. And we're going to connect it like that. And that is an example of an exponential function. A lot of times in math class, we talk about like the real world. Well, exponential functions in the real world, they can model a whole lot of different things. For example, they could model like the population of turtles on an island that are just growing at a really, really fast rate. They could perhaps model like the interest on some sort of investment. So they can do all sorts of things. They're very, very useful. For our purposes today, here's what you would be looking for if you were trying to identify an exponential function from its equation. Anything at all that has an x in the exponent. So the major giveaway is if the function has an x in the exponent, well, then it's an exponential function. Here's kind of some more common forms that you'll see sometimes. Again, anything that has an x in the exponent, that's going to be an exponential function. Generally speaking, there's some exceptions, but generally speaking. So what do their graphs look like? Well, the most common ones are like this or like this. But then you can also sometimes have some situations that are like this or that are like that. It really just kind of depends on what the function says. All right, the table, I like this one. For me, this is one that clicks real quickly, I guess. So here's what I'm going to say. As x increases, sorry, I shouldn't say increase because it could decrease. As x changes, y changes, not by a common difference, but something else. And what is that something else? Well, I want you to pause the video, and then I want you to turn and tell your neighbor, if they're in the same spot of the video, do you see any relationship going on here in this table, in the y values? So as x changes, y changes by a common ratio. So instead of a common difference, it's a common ratio. What does that mean? Well, in the same way that we found the common difference, pick a number, take the number before it, and divide, because ratio means division. 0.5 divided by 0.25 is 2. 1 divided by 0.5 is 2. 2 divided by 1 is 2. 4 divided by 2 is 2. That is a common ratio of 2. And that will help you identify that this is an exponential function. Okay, 2 more examples. They go very quick. I know this video is getting pretty long. Example 2, it says identify function family by equation. Pause the video, see if you can identify these 4. Okay, the first one, this is quadratic. What gave it away? Well, that was an exponent of 2. The next one is absolute value. What gave that away? Well, it was the absolute value symbols right there. The next one, linear. How can it be linear if it's not in the form mx plus b or y equals mx plus b? Because the b value is 0. All right, the last one has an x in the exponent. That must be exponential. All right, next section, and this is what you're going to have to do on the homework today. You're going to have to identify function family by table. Well, the first one, if I look at it, I'm not exactly sure what's going on there. But next, I'm like, 0.25 to 1, 0.25 to 1, and then 1 to 4, and then 4 to 16. Boy, that looks like it is multiplying by 4 the whole way. And it is, therefore, this is a common ratio, which means it's an exponential function. All right, next one. So let's see, we're going down. 4, 3, 2, and then 3, 4. Pause the video and see if there's any of our definitions that say anything about that. Well, what if we go back and look at absolute value? As x changes, the y values change by a common difference up to a turning point, and then the sign change of the common difference, and it continues. Well, this looks like it goes down by 1, and then it goes up by 1, up by 1. I think that is a good candidate to be an absolute value function. That is absolutely an absolute value function. All right, 2 more. This next one, let's see, 0, 2, 4, 6, 8. That looks like a common difference of 2, which means it is linear. Last one, trickiest one of all. So I don't really immediately see any pattern or common difference. So I'm going to have to go -2 minus 1, which is -3. I'm going to have to go -3 minus -2, which is -1. Let's see, where am I? I'm going to have to go -2 minus -3, which is +1. And then I'm going to have to go 1 minus -2, which is +3. Oh boy, I don't see much of a pattern. Let's see if we can find a common second difference. So if I go -1 minus -3, that would give me +2. If I go 1 minus -1, that would give me +2. And if I go 3 minus 1, that would give me 2. Sure enough, that is a common second difference. And the one that has a common second difference, if we go back and look at our notes, that must be quadratic. All right. Oops. Quadratic. Okay, so what are the 4 function types we talked about today? Exponential, absolute value, linear, and quadratic. How can you identify them? Well, you can identify them 3 different ways. Either by looking at their function notation or their equation. You can look at the graph, or you can look at a table of values. Your homework today is actually a hard copy assignment, and the substitute teacher who is there should have that for you. If you have any questions, come see me during seminar. Otherwise, have a great rest of your day.